So my name is Konstantinos Chasapis. I'm a, oh, sorry. Yes. I am a research engineer at Data Direct Networks, and today I will present the work that we did within the work package 4, and it is the integration of parallel I/O library and Flash native accelerators and evaluation of SIONlib with IME. And this work is a collaboration between Jean Thomas Okoaviva, a colleague of mine, and Sebastian Luz from the Jülich Supercomputing Center. So storage is still undergoing a deep revolution with the arrival of flash devices, storage class memory, and of course, cloud storage. The arrival of such devices brings higher level of performance, both in terms of bandwidth and latency, but also brings more opportunities and such as the ability to be byte addressable. The result of this is the need of new software stacks that will either be explicitly designed for Flash, or we have to be highly adapted for such media in order to obtain the performance that such devices can offer. On the HPC side, regarding the computations, users have a long and successful history that are able to extract the best performance from the compute systems. However, this comes often in the expense of low-level analysis and also careful application optimization. This leads in really putting a lot of burden on the application developers in order to improve the performance. On the I/O side, several I/O libraries have been developed, and they're either like generic or targeted for specific users, such as checkpoint restarts, in order to ease the usability of the storage system, and also the portability between different machines. In this work, we pursue a twofold goal. The first one is to help the application developers to keep their focus on the problem that they want to solve without requesting in-depth analysis of the storage system. And the second one is to deliver the highest level of I/O performance using the high-end storage devices. In detail, we evaluate the performance improvement of the integration of IME with SIONlib, in contrast to a classical parallel file system. In the following slides, we will provide you some background information regarding IME and SIONlib, and then we will have our analysis and the discussion. So why do we choose IME and SIONlib? IME is not a fully independent file system, but it depends on a backend file system. IME is meant to accelerate the bulk data using flat storage, but it still keeps the metadata operation at the parallel file system. On the other side, SIONlib is doing exactly the opposite. Is meant to accelerate the parallel file system metadata. The combination between the SIONlib and IME is really a perfect match for high level and high performance I/O in an HPC infrastructure. In the following talk, I will give first some background information for IME and SIONlib. Then I will show you our evaluations, and finally I will conclude the talk. So a few things about IME. IME stands for Infinity Memory Engine, and it is a product from DDN. IME has really lots of features, and within this talk I will not go through details of all of them, but I will only focus on what is important in order to understand the results that I will present later. In a sense, IME is a scale-out flash cache layer using NVMe SSDs that are inserted between the compute cluster and the backend parallel file system. IME is configured as a cluster with multiple NVMe servers, and it handles the I/O traffic, forwarding the request from the client to the parallel file system. The purpose of IME, as I said above, is to accelerate difficult I/O partners, such as small I/O or random I/O, and is also targeted in shared files that have high concurrency by taking advantages of flash device characteristics. One of the advantages of IME is that it is implemented as a thin software I/O management layer, and it shifts the burden of complex metadata operations to the underlying file system. IME, as I said, is not really a full file system, so we really rely on the parallel file system. Is a cache, and this is really important to understand from this talk, and this is why we have to use SIONlib in order to achieve high metadata performance also. IME as a cache, it has a spillover mechanism that is implemented, and it moves the data directly from the IME servers to the parallel file system. IME is fully distributed, it is resilient, it is transparent to the application, and it is based on flash native I/O devices. In the following slide, I'm giving an overview on how is the I/O path from the compute nodes to the parallel file system with the integration of IME. IME is consisting of two parts, the IME client and the IME server. The IME client is installed in the compute nodes of the cluster. In the IME client nodes, the applications are the ones that issue the I/O to the clients. Then the IME client performs erasure encoding between the aggregated buffers to reach the parity configuration. So why we do that is because in the IME, we are able to withstand device fault tolerance. And we do the erasure encoding in the client side rather than traditionally what file systems do on the server side where they use RAIDs. Once the parity is computed on the client nodes, the blocks are distributed in the IME server using a hash method. So they're not like going all of them in a single IME server that might result in a bottleneck. On the server side, if we have fault tolerance configuration configured as an IME server fault tolerance, then the IME metadata are distributing among the IME servers. On the server side, also we have data coalescing. So the user data are being are forming large buffers, and we send large buffers to the parallel file system, and these buffers are aligned in the parallel file system block size. That's why we are able to achieve the maximum performance of the parallel file system. In this slide, I also present another novelty of IME, that it is crucial also to understand the results later, that it is how IME is handling writes. IME is handling writes in a byte addressable manner rather than block-based that traditional file systems do. During each write, we create a fragment that consists only on the bytes that are changed rather than a full block of data that in parallel file systems do. This means that we don't have really to do a lock between different writes in order to reserve the file system block that this write will belong. Rather, for every write, we timestamp it, and later, during a read operation, we are able to virtually render the the regions of the blocks that are being wrote, and we present the latest view. So IME on the client side can be used in various options. We can have the application using high-level I/O libraries that IME can be integrated there, and this is our use case for this talk, that we have SIONlib as a high I/O library, and IME is integrated there. Then IME has native integration with various MPI implementations. Also, IME offers a POSIX interface using Fuse. That means an application can use it without any modification at all. We offer also the IME native client library, that it is similar to POSIX IME interface that provides the best performance of IME. Next, I will give some background information regarding SIONlib. So, sorry for this. SIONlib is a scalable I/O library for parallel access to task local files. The main motivation of SIONlib is that it wants to avoid the metadata operations in a parallel file system that are very costly, and also to avoid single shared file access that can lead to contention, especially when the writes occur in the same file system block in parallel. So how SIONlib does that is that it uses a custom SIONlib file format that maps many logical files in a single physical file. The application then has the task per file picture that the developers need, and internally all these are transformed in a single or a few files. The file access is performed using SIONlib equivalent to standard CIO functionality, and apart from the open and close operations that are collective, all the rest are operations are independent. During the open phase with the SIONlib calls, the developer is able to specify which low-level I/O library will be used to perform I/O. Of course, SIONlib can be used as a replacement to standard I/O APIs such as POSIX. In this slide, we illustrate the internal structure of a SIONlib file. So internally, the physical file is subdivided into a sequences of blocks, which themselves contain one chunk of data belonging to every logical file. In case the amount to be written in one file is known upfront, it can be specified while opening the file, and it is allocated sequentially. If the chunk size is not known upfront, then SIONlib just selects a sensible default when the file is open. And if it needs to write more than the default that SIONlib selected, then another chunk is being allocated, and the writes and reads between the different chunks are handled transparently from the application, and SIONlib handles that. SIONlib also uses information regarding the block size of the underlying file system, and it tries to always have chunks aligned to file system block size in order to avoid tasks accessing the same block and ensure contention-free access to file system blocks. So that is all for the background information that I would like to give for these two technologies. And I'm moving to the evaluation part. So in this figure, we visualize the integration of SIONlib and the IME. So SIONlib has internally 3 layers that forward the IO requests from the application to the supported interfaces. The SION generic API is the one that it is being exported to the application developers. Using flags during the open call, the application developer can select the IO interface that would like to utilize. And in the serial layer, that it is the bottom layer, the IO requests are forwarded in the desired IO interface. So part of this work was to integrate the IME native IO API to SIONlib. As I said earlier, with the IME native, we are able to achieve the maximum performance that IME can offer. In the background slides of IME, I had also mentioned that IME exports a POSIX interface using Fuse. And of course, we could have used SIONlib directly with this POSIX Fuse implementation of IME. However, the Fuse implementations comes with performance drops. And in this slide, we are illustrating why we have these performance drops. So using the IME Fuse, we have, of course, to use the Fuse kernel module. That means that we have to cross the kernel 2 times in order to serve an IO request. Also, the Fuse kernel module has its own limitations. And for example, it does not allow the parallel lights in a single shared file. And this greatly impacts the performance when we use IME with Fuse. We will see it later in the results. As for our evaluation methodology, we perform our evaluations using PARTEST, that it is a benchmark provided as part of SIONlib, and it can exercise different IO patterns. PARTEST can be parameterized and you can tune the type of IO that you would like to perform, a single shared file that it is like the SIONlib format, or a file per process. Then we are able to tune the chunk size, that this defines the contiguous file area assigned per task. The buffer size that specifies the amount of data that each IO call transfers, and also the interface to be selected for the low-level IO calls. And for us, we evaluate POSIX and IME native. In our evaluation, we include the experimentation with different chunk size and buffer size to see if there is like a sensitivity of performance in relation to the low-level interface used. Our analysis is focused on the right path, since this is the most demanding from the application perspective during the checkpoint phase, which is typically IO intensive operation. And for our experiments, we have 3 different use cases. The first one is using the parallel file system, the Spectrum Scaler version 4, formerly known as GPFS, without the use of IME. Then the performance of IME without any modification in SIONlib using the Fuse interface. And last, the improvements that we get when we have the SIONlib integrated with the IME native interface. Here are some details on the testbed setup. All the experiments were conducted at the Jülich Supercomputing Center. The IME installation there consists of 54 IME servers. The servers are set up with IME node failure. So there is like extra copies of IME metadata when we write something to the IME servers. And also we have a 9+1 parity encoding to support storage device failure. The compute nodes are equipped with dual Intel CPUs with two 24-core CPUs and 96 gigabytes of RAM, and in InfiniBand NDR Connect X4 that allows up to 12.5 gigabytes per second network transfers. For all the experiments, we write 128 gigabytes per node, that it is sufficient to fill the caches and also provide stable results across multiple runs. The system is actually used during the runs. It is a production system, but we have monitored IME, and we see that the results that I will present are not really interfered with other jobs that are running in parallel. This is the first figure that I will present, and it illustrates the aggregated write throughput reported by Paratest when we vary the number of processes used, the so-called strong scaling, from 1 to 48. 48 is the maximum cores that a single Joule node has. And this test is run on a single client node. Both the parameters of chunk size and buffer size from SIONlib have been selected to deliver the highest throughput. On the y-axis, we have the aggregated throughput. Higher is better, and in the x-axis, we have the number of processes. As we can see, a single IME process achieves 80% faster when we use the IME native than the IME fuse, and achieves 40% faster with comparison to Spectrum Scaler. Spectrum Scaler is able to achieve the maximum performance of 5 gigabytes per second with 16 processes. And IME native is able to reach 9 gigabytes with the same configuration, resulting on an improvement of factor of 1.8. IME native performs like best using 12 processes and is giving us around 9.1 gigabytes per second, that it is only 30% less than the theoretical maximum that the network interface offers. This figure accounts also for the extra block that we have to transfer due to the parity calculation we do on the client side, but also on the performance impact that we have on the IME server side, that we have to replicate IME metadata to ensure IME server node tolerance, fault tolerance. In the figure here, we observe that IME performance does not really increase when we use more processes. The problem with that is that the fuse implementation does not allow parallel files, parallel writes in a single shared file. There is a mutex there on the module, and we are trying to convince the community that they should remove these mutex, or at least give us the option to bypass it when we have IME, but so far we have not really resolved that. In this slide, we are presenting the weak scaling, that it is how the write throughput improves when we use more nodes. We take the best configuration of the previous experiment, that it is like 16 processes per node, and we have also the best chunk size and buffer size to bring the best results. Again, in the y-axis, we have the aggregated throughput, higher is better, and in the x-axis now, we have the number of nodes used. IME native performance scales linearly with the number of nodes, doubling every time that we double the number of nodes. And we reach 71 gigabytes per second with 8 nodes, that it is again similar to a single node, only 30% less than the theoretical maximum. We continue to deliver faster throughput with 16 nodes, but the improvement drops, and now it's a factor of 1.38 in comparison with 8 nodes. Spectrum scaler performance also improves when we move from 1 node to 2 nodes by a factor of 1.48, but the trend does not continue when we move from 4 nodes and on, and there is improvement only of around 20%. And with Spectrum Scaler, we are able to achieve the maximum of 17 gigabytes per second with 8 nodes. And then when we add more nodes, the performance also drops. IME Fuse improves by a factor of 1.7. It's really hard, I think, to see it in this figure. And when we double the number of nodes, but again, the performance of IME Fuse is really poor since we have the mutex lock in the Fuse module. In the next slides, we will present some experimentation that we did with the SIONlib parameters of buffer size, transfer size, and the chunk size, and we will see the implication on the actual IO library that is being utilized, IME versus the Spectrum Scaler. For this figure, we vary the number of bytes transferred, and we vary between 4K to 1 megabyte. And all these tests are executed in one compute node with 16 processes, sharing a single file, and the chunk size is constant of 2 gigabytes. In the y-axis, again, we have the aggregated write throughput, and in the x-axis, we have the buffer size in kilobytes. As we can see, IME native is not really impacted at all with the amount of data that are being transferred, where for GPFS or Spectrum Scaler, it requires at least 64 kilobytes transfer size in order to reach the maximum throughput of 4.8 gigabytes, and performs really purely when we have a buffer size that it is less than or equal than 32 kilobytes. In these slides, we illustrate the importance of the chunk size. And what we do is that we vary the chunk size from 16 megabytes to 124 megabytes, 1 gigabyte. The chunk size, like if you remember, is the amount of data each file will have as a contiguous in the single shared file. And all the rest of the parameters are the same as in the previous experiment. Y-axis, again, we have the aggregated write throughput, and the x-axis is the chunk size. As in the previous scenario, we see that IME is not impacted at all from the chunk size, where the Spectrum Scaler, again, it requires a minimum of 256 megabytes in order to deliver the maximum performance. The last slide that I would like to present on our experiments is comparing the IME Fuse performance with the IME native. In this scenario, what we do is that we use partes with a configuration of file per process. So it's different than what actually SION is meant to do. But with this test, we are able to bypass the mutex lock that the Fuse module is implementing. So, and we can just see the improvement with IME native in contrast to IME Fuse. So in the y-axis, again, we have the aggregated write throughput, and in the x-axis now we have the number of files and the number of processes used. This test has a file per process. And we see that we always have better performance with IME native, and as I saw before, we know the reason. Since using IME native, we don't have to cross the kernel at all, and we eliminate this huge IO stack that it has to go through in comparison to IME Fuse. And with that, I would like to conclude this talk. So what we presented today is that we managed to do an integration of IME and SIONlib, and this integration was done with, let's say, a code design, and the application is able to benefit from both the IME advantages and the SIONlib advantages without any code modification. The improvements in contrast to the parallel file system is 1.8 times for a single node and up to 6.1 times with 16 clients. And we also see that with our solution, we don't have any interference in selecting the chunk size and the transfer size. We conclude that such IO libraries with storage devices integrations are really beneficial and are much preferable to HPC IO, since POSIX is really hard to optimize. And with that, I would like to thank you for your time, and please ask any question.
Thank you very much, Konstantinos.